Hello, my name is Arij. I'm presenting my project for pattern recognition EEL 6825 behavior recognition in fish using accelerometer data. Basically, the aim for my project was to recognize a particular pattern in a fish called an escape movement, and the fish that I was dealing with is Calopus oleoptis. It's an escape movement that this fish demonstrates when it comes across a threat or some sort of danger. Right. So my aim was to use accelerometer data to basically recognize this characteristic pattern in the fish. So this is what my data set looked like. It consisted of 3 accelerometers, each with 3 channels, so X, Y, and Z. And I was supposed to calibrate all these 9 channels to identify the sensor that was supposed to be most discriminatory for the motion that I wanted to classify. So like you can see, this is for the tail sensor. That is the index point where the calibration of all 3 sensors occur. So that's all the 9 channels. And I plotted a spectrogram to find that time point with high frequency, high amplitude calibration point. That was the event where the entire accelerometer had to be truncated and had to be synchronized with the videos that were used to label the dataset. And I had to do the labeling on my own. So that was a very challenging thing to do. And here is a clip of a video of how the experiment was done. So here basically the escape moments and the routine events were triggered. I hope the video works. It's been giving me a tough time. This is actually a video of the escape event that actually happens. I have a feeling. Okay, so it's not working. So it's basically, yeah, so you see that, okay, there's more actually. So there's a tail flip that happens, and then the fish glides, and then it turns. So that entire sequence of event is called an escape moment, and it lasts for around 2 to 3 seconds. So since this motion was a lot of tail motion, I made sure I used the tail sensor data instead to classify this event, and I used only the axis that was around the lateral axis, because that's where the motion of the tail is along. So it'll be very easy to discriminate. And it actually was very easy to discriminate and identify this particular event, escape event, from the routine movement. So I plotted the XYZ channels to see how the fast start event would look like in the tail sensor data, and you'd see this is where at time 0, that's where it initiates, it glides, and then it turns in the end to mark the end of the escape, the entire motion. So that was very interesting to see. So I looked at across all the signals, and I noticed that X was the most relevant feature. X channel was the most relevant source of information for doing my classification. So I basically segmented the entire data set into windows of 3 seconds, non-overlapping windows, and I extracted features for each of them, and then I labeled them simultaneously to get a label data set, a validation data set, and a training data set. Sorry, yeah, so the wrong order, but yeah, 60s to 20s to 20, because the events are very less. They only accounted to around 6,953 seconds. And I extracted features like mean, standard deviation, range, and RMS values. I ended up using only the first 3 features for my binary classification, because the RMS value is actually not contributing to any sort of prediction. So it was just being a redundant feature. So I eliminated it, and I noticed that when I plotted my range with my mean, it was a very obvious clustering of events, and you'll see that the frequency of fast start events or the escape events was very less, right? And even then, my binary classifiers were able to train on it and classify. So KNN gave a perfect accuracy. This is the RSC curve for KNN. SVM, I've demonstrated its accuracy in one of my videos, and there was a slight probably misclassified 1 escape event, but otherwise it showed close to 100% accuracy. So this seemed like a very easy task comparatively. I mean, the processing took a lot of time, but then I thought, well, how about if I try to discriminate? How will it work if I try to discriminate turn from the routine events? So there were turns besides the escape events that I wanted to classify. So I tried to do multi-classification, and I tried to extract more features. And autocorrelation coefficients have been known to be very good features for time series events. So I extracted autocorrelation coefficients that increase the dimensionality to 24. So I tried to do a PCA analysis and see which features were important and contributed to the variance of my data set. And if you notice, the principal variability of the first 3 components was already accounted at 92%. So, sorry, 98%. So I discarded the autocorrelation coefficients and went ahead with my multi-class classification using only these 3 features. And I also this is just basically a plot of my 24-dimensional data along the axis because of the linear transformation that PCA does for dimensionality reduction. And then I try to tune my parameters for multi-class classification using different SVM models, right? So I use a linear SVM model and I use a quadratic and a cubic SVM model. And I plotted these parameters, the accuracies for each of them on validation and training set. And I try to see which one was the most optimum one. And linear proved to be the most optimum classifier in terms of when you're talking about the polynomial kernels for SVM. And then I noticed that if I use a Gaussian instead, a Gaussian gave a good accuracy on both validation and testing accuracy, but it gave a better ROC curve for class 3, which was my aim of multi-class classification, trying to identify turns, right? So the ROC curve for Gaussian curve was much better than for a linear SVM. So like the area under curve here is 0.52, this one is 0.82. So there's a drastic change if you change the SVM function. So the project, these are my results. Basically, I've given a better summary in my report, of course. But I learned a lot of basic traditional machine learning, feature selection, feature engineering, data processing, and how difficult it is to manually label the data set, and how an unbiased data set can really hamper your frequency. But if your features are good enough, it honestly doesn't matter. So I'm really glad I took this class, and I thank you for all the lectures Dr. Wu put up, because I was an online student, and I learned a lot through those lectures. Thank you so much. I hope you enjoyed my presentation. And I should stop.